In this video, we're going to talk about how resistance and resistivity can be affected by temperature. When you pull out a engineering table or the CRC, the Chemical Rubber Company Handbook, you'll find that it gives you the resistivity of a material, but it's for a particular temperature. For instance, maybe it's at 20 degrees Celsius. But you're going to run your device at some other temperature. For instance, maybe it's in the back of a television set and you know it's going to be operating at maybe 70 degrees Celsius, or maybe it's 35 degrees Celsius. How do you account for and find the correct value of the resistance if you don't know the correct value of the resistivity? Well, we're going to have to get the correct value of the resistivity and figure out what that value is. Well, it turns out that resistivity, like densities of a material, can in fact go up or down with change in temperatures. But for most things like metals, certainly not exotic things like semiconductors and such that quantum physicists may play with, but things like metals, copper, gold, aluminum, those almost without a doubt increase with resistivity with increasing temperature. And now we can understand that using our little microscopic model. We can think of the little ions that we had before, the little positive charge with whatever electrons they had still. They're kind of left here all through the material. And we kind of ignored them. But in fact, they have some energy, so they're vibrating back and forth, 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 back and forth. You can think of them like little doors or those slamming giant pistons that you see in sci-fi movies. And these poor little electrons are trying to go through there without getting bounced around by these ions. And the faster those ions move, like you running down a hallway and having a bunch of doors shut, open, close, open, close, open, close faster, you're going to find it harder to make it down because you're getting banged out of the way or blocked by these closing doors. This is the same thing that can be thought of as happening to the charge carriers as they're moving through this metal, which you can think of the doors being these positive ions. Okay? Now, what we want to do is we want to find a way to mathematically describe that and get us our value of resistivity. So as temperature increases, resistance or resistivity of material for most metals and such increases. Now the secret for finding a mathematical solution to our problem is something that's used a lot of places in engineering and physics, and this is called Taylor series approximation. We're going to write any analytical function. By that I mean a function that's continuous and single valued, finite, a function that we can take its derivative. In other words, it may be some function like that, but at each point it's finite and I can draw a slope across it and take derivatives. Almost anything in physics or engineering has that property if you think about it. You know, if you were plotting position with the time, you can't have a position that goes along like this and then goes up like that because it'd have to have an infinite velocity change between here and here to get from this location to that location. If this was velocity, you can't have velocity like this, say at 1 meter per second, and then in no time switch to 2 meters per second because it would have a derivative that doesn't exist and basically require an infinite acceleration. Those things just don't happen in the real world. Now there are some things that have like 1 over r squared dependence. Those can be handled by using what's called the Lorentz series, and you'll discover those in your advanced engineering or physics math methods course. But for now, we're going to deal with the fact that the resistivity is a nice smoothly varying thing, although it may not be linear, it may be some sort of curve. And what we can do with that is we can write that as a function as we change the temperature of some constant plus some constant times delta T plus some constant times delta T squared plus some constant A3 delta T cubed so on and so forth. And math tells us that you can do that for any function that's analytic as long as you keep an infinite number of terms. It even tells us how to find the values of that. You take the nth derivative of the function, evaluate when delta t goes to 0, divide by n factorial, and that's actually the coefficients that need to go here. Now that's what a mathematician or theorist does. Our only interest in it is because it's true, we know we can do it. So they've actually done this in the book back when they did thermal expansion, when they did volumetric expansion. In fact, you see it throughout engineering courseworks when you see courses that say linear circuit analysis, linear material analysis, linear strain analysis. Anytime they said the word linear, they're taking advantage of this, making small changes and only keeping the first two terms. If you see a course nonlinear, then they're keeping more of these terms. What this means is I can do this type of thing experimentally. And I can experimentally find these coefficients rather than do them with derivatives in math. And that's what I'm going to do here. So if the temperature can be represented this way, then I know that I should be able to write that rho is equal to the temperature when I don't change it, that's rho naught, plus some coefficient A1 delta T, plus some coefficient A2 delta T squared, so on and so forth. And using the fact that delta T is this T minus T naught, and limiting ourselves to only small temperature changes, then rho of T must be approximately the original value in the table plus some small change that depends only on the first power of delta T. Now, what we want to do is we want to find out the percent change in essence. So I'm going to factor rho naught out of both sides. Rho of T is approximately rho naught times 1 plus A1 over rho times delta T. But A1's a constant, and this rho naught here, that's a constant. So two constants divided is just another constant. So I could rewrite this as rho naught times 1 plus alpha delta T, where alpha is A1 over rho naught. Now what is this saying? This says that I can go and plot this thing as a function of temperature. And maybe it does follow some curve. But I can take a value here, rho naught, and at that location, I can fit this curve for short distances with a straight line, whose slope is alpha times rho naught. This alpha has a name. It's called the temperature coefficient of resistivity, and it's given in the table along with the value rho naught. Let's show you how this actually works on a problem. So, from the books, we find for silver has 20 degrees Celsius, has a resistivity of 1.47 10 to the minus 8 ohm meters, and a temperature coefficient of resistivity of 3.8 10 to the minus 3. So, rho naught 1.47 by 10 to the minus 8 ohm meters, alpha 3.8 by 10 to the minus 3 centigrade to the minus 1. Rho naught times alpha. Well, let's first tell you what before do. Let's do alpha delta T. Alpha delta T is 3.8 by 10 to the minus 3 C to the minus 1 times 80 degrees C. That's the change from 100 minus 20. We're going to punch that in the calculator. And we get for a value here of 0.304. That means that this thing has a 30% change in its resistivity over this temperature difference. To find the resistance now, we put in 1.47 by 10 to the minus 8 ohm meters and multiply that resistivity by 1.304. 1.47 second e to the minus 8, and we get 1.92 by 10 to the minus 8 ohm meters. So that's the new resistivity, and I can use that resistivity now to calculate the resistance for that particular material at that temperature. So very useful little formula to know. All right, I'll see you on another video.